Hello there everyone, my name is Daniel Arnellis, and today I'll be walking you through problem number 11, web work number 5. The problem we have is an electromotive force E of t, different at different values of t, is applied to an LR series circuit in which the inductance is 20, the resistance is 2, and the initial condition is I of 0 equals 0. So, to start off with these series circuit problems, we always start with Kirchhoff's voltage law, which basically says that any electromotive force over the circuit is equal to the sum of the voltage drops. And here, we only have an inductor and a resistor, and we know what their voltages are. So we just pop that right into the equation, L di dt plus IR. But we can't simply solve that yet because we have two different equations at two different values of t. So we got to split it right down the middle. I put 0 to 20 on the left and over 20 on the right. Now, we plug in our 120 right here for our E of t, because we're between 0 and 20 for t. Divide by 20 to get an equation we recognize a little better, the di dt all alone, and a independent variable right here multiplied by a coefficient. Alrighty, so we know that our P of t is the coefficient, which is 1 over 10. We find our integrating factor here, and that would be e to the integral of our P of t dt, which is e to the t over 10. Multiply that by both sides of the equation, and we know that this side of the equation is equal to the derivative of our integrating factor times the independent variable, which is then equal to the left side of our equation here. So we integrate both sides, and we find that e of t, e to the t over 10 times I is equal to 60 e to the t over 10 plus some constant. We divide e to the t over 10 on both sides. We find that the current at any time t is equal to 60 plus some number we don't know yet, times e to the negative t over 10. Now here, we need to use our initial value, which was I of 0 equals 0. We substitute that in, and we find c equals negative 60, and we get our final equation. I factored out the 60, I just like it that way. You obviously don't have to if you don't want to. And that is our solution. The second side goes mainly the same way. You substitute the 0 for the E of t instead of 120, so here it's 0. Divide by 20, find your P of t, your mu, integrate both sides, of course. Grand of 0 is just some constant instead of, a value plus a constant. So divide both sides by e to the t over 10, and you get I of t equals ce to the negative t over 10, just the constant times our integrating factor. Now, the problem I ran into several times and ran in circles was I accidentally then tried to use this initial value here to find the constant. You cannot do that because for this value of t, it doesn't start at 0. It starts at 20. We're using the equation for our E of t equals 0 at a different point in time. So we have to use our previous equation to find I of 20, the starting value for our next equation. It doesn't have to be at 20, it could be anything over 20, but I just used 20. So we find that to be 60 times 1 minus e to the negative 2. And using I of 20 for our new equation, we then set it equal to our old equation, and we solve for c. Then we plug it back in to our new equation and find our second answer. That's how you do it. Have a good day.